Welcome, class. Today we are going to begin our discussion of Chapter 9. So, in this chapter, we are going to be looking at the electrons within the atom. Now, we've mentioned earlier that electrons are really the key to element behavior, right? So it's the electrons that really control the chemical properties and chemical activity. So in this chapter, what we're going to try to do is to have a better understanding of how the electrons exist within the atom and then connect that to the behavior and chemical properties. Now, in order to do this, we are going to look a little more in depth at electromagnetic radiation, or what we know as light. We're going to explore two models that help us understand the electrons within the atom, and we're going to learn a couple methods for organizing the electrons within the atom. Now, in today's class, we're going to focus on electromagnetic radiation and one of these models. So, to get us started as a basic introduction, right, one of the things that we've observed, right, through Mendeleev and through his periodic law and through the organization of the periodic table and general chemical observation, right, is that elements behave differently, right? So we can observe that things like hydrogen and the alkali metals and the halogens, right, are very reactive, right? They react readily. While other groups on the periodic table, such as group 8, the noble gases, right, are quite unreactive, quite inert. Well, what explains this difference? Well, it clearly has something to do with the electrons, because we know the electrons heavily influence the reactivity of elements. So Mendeleev's periodic law and his periodic table help sum up these observations, right? So when the elements are arranged in order of increasing atomic number, as they are in our modern periodic table, we see certain sets of properties recur periodically, right? So the whole point of the periodic table was that Mendeleev organized so that the groups, right, the columns, displayed this periodic nature, right? Those are the elements grouped together that have these similar properties, and they repeat every so often. So what about the electrons allows this repetition, or how do we explain this repetition, this periodicity? Well, some models and theories will help us explain why this observed behavior occurs. Now, the two theories that we are going to look at, or maybe you want to call them models, are the Bohr model, right? This was an earlier model, and our more modern model, the quantum mechanical model. Now, it should be noted that both of these models are actually based on a quantum mechanical idea. The quantum mechanical model is just a bit more advanced. So these models help us explain how electrons exist in the atom and how these electrons affect the properties and behavior of the atoms. Now, you will see lots of names when we talk about these things. These are some of the most famous physicists to ever work on some of these problems when we come across it. People like Niels Bohr, who developed the Bohr model, or Schrödinger, probably most famous for his thought experiment Schrödinger's cat, but was heavily involved in development of quantum mechanics, along, of course, with Einstein and the others that helped develop these theories. Now, all of this development was going on in the early 1900s, right? So this is when all of this development was taking place. Now, one of the most interesting aspects of this that we won't have time to delve into a whole lot is that they were quite mystified and bewildered in some ways, and sometimes even not really accepting of their own work, right? It was so outside what they had known that they had a hard time accepting the validity of it, even though that's where the experimentation led them. And what eventually this leads to is something that's sort of the hallmark or the basic underpinning of all of these theory is that electrons or quantum particles in general exist in a wave-particle duality. And all of this essentially means is that they can behave like a wave in some instances or behave like a particle in other instances. But we can't observe both of those types of properties at the same time. Now, before we can jump straight into looking at electrons in the atoms, we need to sort of set the stage by looking at what's called electromagnetic radiation, or what we commonly know as light. Now, some of the reasons we look at this is because the interaction of light with atoms helped to shape these models, right? It was, one of the things that we looked at. So these things are interconnected in the theory. So what we should understand is the light. And when I say light, we typically mean visible light. What we see is one form of what's known as electromagnetic radiation. And all of that means is that this is any form of energy that travels through space at a constant speed of 3 times 10 to the 8 meters per second, or what we more commonly know as the speed of light, right? So again, this is 3 times 10 to the 8 meters per second, or 300 million meters per second. To put that in a little other context, that's equivalent to about 186,000 miles per second. So really fast, right? Now, one of the usefulnesses of looking at light is that light also displays this wave-particle duality, right? Where it can have properties of a wave, but also aspects of particle property. So light, like any wave, right, has certain fundamental properties, right? Light has a wavelength, right? So now what is wavelength? Well, wavelength, which you'll see abbreviated in a couple ways, right? The symbol, right, looks like this Greek letter, which is lambda. Looks like kind of like an upside down Y. And wavelength is simply the distance between adjacent wave crests. So as we see here in the picture, right, our wavelength is from this crest to this crest, or any crest, any two adjacent crests, right? That is what we define as the wavelength or the lambda. And it is a property of a light wave, right? So you can have waves with varying wavelengths, and we'll talk about that as we go through. Now, these waves carry energy, and we'll talk more about that energy a little bit later. Now, when we think about light, one of the aspects that immediately jumps to our mind is colors of light, right? So when we think about visible light, we think about it as having colors, right? We can see white light, we can see red light, we can see blue light, green light, etc., right? So what does that mean? What does the color of light tell us? Well, first things, white light, this is light that might be produced by the sun or certain types of light bulbs, contain a spectrum of wavelengths and therefore a spectrum of colors. So another way to sort of view this is that white light is that we're seeing all the colors all at once, right? And we do that, our brain interprets that as white light. So when all of those wavelengths come into our eyes at once, the brain says that's white light. Now, that white light is made up by a spectrum of colors or a spectrum of wavelengths. Now we can see these individually ones, right? We can see red, orange, yellow, green, blue, indigo, violet. These are sort of the major colors, and all the shades in between, right? Now, when white light is passed through a prism, whether that's a glass crystal or a raindrop of the right size, the colors are spread out or separated, and we get the rainbow effect, right? We see a rainbow in the sky, or you can see rainbows coming off of crystals or gemstones when sunlight passes through them. We see little rainbow effects, right? That's what we're seeing here. Now, if we look at the sort of the extremes of the light that we can see, at one end of that we have the red light. Red light has the longest wavelength that we can perceive, and that's about 750 nanometers. The shortest light that's visible is what we would see as a violet light, and it has a wavelength of right around 400 nanometers. Now remember from our metric system that 1 nanometer equals 1 times 10 to the minus 9th meters, right? And this is something that we're going to want to know, and we're going to want to be able to look at as we go through this. So you're going to want to remember that so that we can convert from meters to nanometers. Now, when we see stuff, right? When we see colors, right? When we look at something, why does it appear certain colors to us, right? Well, as you might imagine, it has to do with the wavelengths of light that are coming off of that. Now, they're not being emitted by that, right? Everything that's colored isn't emitting light. What's happening is white light, say from the sun or from the forms of light, right, are hitting that object, and certain wavelengths are being reflected and certain wavelengths are being absorbed. Now, the wavelengths that are reflected is what we see. So when something looks, for example, red to us, that means it's reflecting red light but absorbing other colors of light. So all we see coming off of it is the red light. And so that's how things appear different colors to us. Now, when we diffract, right, let's remember it's a continuous spectrum, right? So it isn't just these 7 colors, right? Red, orange, yellow, green, blue, indigo, violet, right? Those are the major points, the reference points, but it is a continuous spectrum of shades going in from one to the other. So, but to help remember the order of these, right, we have the acronym Roy G. Biv, or red, orange, yellow, green, blue, indigo, violet, where red is the high end, so this is high wavelength, and this is low wavelength. So remember, to see something in color, the materials or the chemicals, the dyes that we've added to this material to, say, make it red, right? When we add red dye, what we're doing is that red dye contains a chemical that reflects red light and absorbs other colors of light. Now, one last thing about color, right? Some people always ask, black, right? When something appears black, it means no light is reflected, or very, very little, right? So it means that material is absorbing the visible light, and so we see an absence of light coming off of it, and our brain says that's black. Whereas if something is white, it means it's reflecting everything, and we see what is essentially white light coming off of it. Now, another fundamental property of waves that is closely related to this idea of wavelength is what's called the frequency. So the frequency is symbolized by the Greek letter nu, which kind of looks like an italicized V, right? But it's pronounced nu. And the frequency is the number of waves what we might call crest. Sometimes these are called cycles, so it's the number of wave crests that pass through a point in 1 second. So the idea is, if we were standing still and we at a point, we were staring at a point, if we counted the number of wave crests that passed there in a second, that would tell us the frequency, right? So sometimes we hear this called the frequency in terms of cycles per second, or waves per second, right? That's what we're talking about when we talk about the frequency. Now, the connection between wavelengths and frequency is that they are inversely connected or inversely related to one another. So what that means is one goes up, the other one goes down. So for example, the shorter the wavelength, right? So if I have a wave that looks like this, where the part of my art here, where the spacing of the waves is very close, right? We're going to see more waves per second, right? It's going to have a higher wavelength. Whereas if I have a wave that has a longer wavelength, right, we're going to see fewer crests pass by in that same second. So when I have a low wavelength, I get a higher frequency. If I have a longer or higher wavelength, I would get a lower frequency. So that's the inverse relationship that we're talking about here. Now, that's the wave nature. Right? But in the early 20th century, Einstein and others discovered that light can also be viewed as a stream of particles, more specifically, energy particles, right? So a particle of light was termed a photon. And so what we think about photons are as a packet or particle of light energy. So one way to view these is sort of a wave that is a continuous stream of these photon particles, right? Where each of these photons contains a certain amount of energy. Now, how much energy? Well, the amount of energy depends on the wavelength, right? Now, it also depends on the frequency, but because the wavelength and the frequency are related, but we're going to talk about it in terms of the wavelength. So the idea is that the shorter the wavelength, the higher the energy. So if we kind of put this together, right, if we have short wavelength, so that means the waves are really close together. We saw in the last slide that means we have a high frequency, but it also means we have a high energy. So short wavelength, high frequency, light has higher energy, right? As opposed to longer wavelength, lower frequency, that's going to be lower energy photons. So invisible light, violet light, right, is the most energetic. Red light is the least energetic. So to summarize all of this, electromagnetic radiation is a form of energy that travels through space at a constant speed, right, that speed of light, 3 times 10 to the 8 meters per second, and can exhibit both wave-like and particle-like properties. The wavelength of electromagnetic radiation determines the amount of energy carried by one of its photons. The shorter the wavelength, the greater the energy of the photons. And the frequency and energy are inversely related to the wavelength. So both frequency and energy have that inverse relationship to wavelength. Before we leave the idea of electromagnetic radiation, let's look more fully at the electromagnetic spectrum. So what we want to point out here, or what we want to observe here, is that electromagnetic radiation is a large array of types of light, or types of radiation, if you will. Whereas visible light is just a tiny little fragment or a tiny little segment of a much larger spectrum of light. And so we're going to take just a few minutes here to look at some of these different regions of the electromagnetic spectrum and sort of associate them with things that we've already, maybe heard of at some point. So we're going to first start here at the high energy side of electromagnetic radiation. So over here, right? So this is going to be your high energy, right? If you look up here, very low frequency, or excuse me, very high frequency, low wavelength, right? So this is your high energy spectrum. So the highest energy forms of electromagnetic radiation are sometimes called gamma rays. So gamma rays are produced by the sun, by stars, and they're one of the properties that are given off by radioactive decay. So when certain elements that are unstable, if radioactive, they will decay and they will give off radioactivity, and one of the forms of that radioactivity is gamma rays. Now, gamma rays are quite dangerous to humans, right? They can damage biological tissues, kill cells, etc. Right? You may have heard them associated with medical treatments, right? That we commonly refer to as radiation therapy, right? The idea of radiation therapy is we're directing gamma rays at a tumor in order to kill that tumor, right? To use the idea that it can kill biological tissue to our advantage. Now, as we move a little bit further toward longer wavelengths, we hit X-rays, right? Now, everybody's familiar with X-rays, right? And their uses in medical treatments, right? So X-rays have the ability to pass through many substances that would block visible light, like soft tissue, skin, but not through harder substances like bones and some organs, and so they can be used to image or to produce images of those harder types of biological tissue. So X-rays, kind of like gamma rays, do have the ability to damage biological tissue. And so we don't just give X-rays for fun, right? We tell certain people that are more susceptible to avoid X-rays, like pregnant women, other people that, maybe, have higher susceptibility. We shield people from, if they're administering X-rays, or we use lead vests to isolate where the X-rays are being targeted. These kinds of things. Now, again, move a little further, closer to the visible, we hit ultraviolet light, or ultraviolet radiation. This is, of course, most commonly associated with UV light from the sun, right? Now, the sun is, of course, giving off white light, right? It's giving off more than white. It's giving off all of these wavelengths, essentially. But most of these, especially the dangerous ones, are shielded out by our atmosphere. Some of the ultraviolet light comes through the atmosphere, of course, and we protect ourselves from exposure by using sunscreen, sunglasses, things that will shield out the ultraviolet light. Now, of course, ultraviolet light can damage biological tissue, not nearly as much as X-rays or gamma rays, but this is what leads to things like sunburn and potentially with high levels or repeated exposure, can cause cell mutations and lead to things like skin cancer. At this point, we get to visible light, right? These are the light that our human brain can associate or can observe, the human eyes can observe, and this is what makes up our frame of reference, right? This is what we see, right? All of these other types of electromagnetic radiation are, of course, invisible to us. Now, as we move, again, to the longer wavelength side of visible light, so we move past the red, we move into much lower energy forms of electromagnetic radiation, right? And forms of energy that no longer pose a threat to biological tissue. So the first region here is what's known as infrared light. Now, infrared light is essentially what we know as heat light, right? Or we associate it sometimes with heat, right? So when you put your hand over a hot object and you feel heat, that's infrared. We use things like heat lamps, right? Heat warmers, like to keep food warm in a restaurant, right? Those are infrared. Infrared is also very commonly used in remote controls. Line of sight remote controls shoot out a beam of infrared light, and that's detected by some detector. It's also used very commonly in our application of what we think of as night vision or heat diagrams, where we can sense heat being given off by objects and that creates an image to us, right? Versus where no heat is being given off, right? That's all related to infrared radiation being emitted. And then, of course, we get into microwaves. Okay? Microwaves are, of course, famous because of microwave ovens, right? And essentially, that's what we use them for anymore. They used to be used a lot for communication. They're still used for things like radar and some very specialized forms of communication. But in a microwave oven, for example, what makes microwaves useful to do this is that they are at the right wavelength to excite or agitate, if you will, water molecules. So when water molecules are exposed to microwaves, they get very energetic. They start to move very rapidly. They start to vibrate very rapidly, and this produces heat, right? They warm up, right? And so it's essentially we are heating food by heating up or exciting the water molecules. Now, beyond microwaves, we get into the longest form, lowest energy form of electromagnetic radiation, and this is a large region which we just call radio waves. And radio waves are used to transmit communication signals in all sorts of different forms. We know some of them, and I'll just mention a couple of them, right? AM radio, FM radio, cell phone, TV signals, and other forms of communication. All are broadcast in this radio wave region of the electromagnetic spectrum. So we want to sort of broaden our view of what electromagnetic radiation is and how it can sort of encompass a whole lot of things that are invisible to us, but still are part of this same category of energy.